All right, guys, Mr. Antonucci here, and we're going to be jumping into section 6, and we're going to talk in this video about integrating a function that contains a quadratic expression. So sometimes an integral that contains a quadratic expression can be found using substitution. So for example, if you look at the two on the screen, for the first one here, if you let u equal x squared plus 5, then du equals 2x dx, and you can adjust for the 2 and you would get your u substitution there. For this second one, I'm not going to work the whole way through it. If you let u equal x squared minus 10, then du is going to be 2x, and then you can, I forgot the x here, 2x minus 10 dx, and then you can rewrite that as 2 times x minus 5 dx, and then you can proceed with the substitution there. But for integrals containing quadratic expressions, you want to always first check to see if substitution can be used. But sometimes it doesn't work, and I'm going to show you some methods here. One of them is by a method called completing the square. So if we're going to look at this example here in a second, integrals that have the form ax squared plus bx plus c, where a is not equal to 0, of course b and c are real numbers, you can complete the square like this. So the first thing you want to do is factor a out of the first two terms like this. So ax plus b over ax plus c. Okay, and then you want to take half of b over a and square it. So half of b over a and square it. So you would have b squared over 4a squared. And then what you're going to do is rewrite that as, so let me just put this in here. So you'd have a times x squared plus b over a x plus, now you're going to add this inside the parentheses here. So it's be b squared over 4 a squared, okay, plus c, and then you have to subtract what we just added because of the additive identity. But be careful here because it's going to be a b squared over 4a, because this a squared is going to cancel with this a technically if you were to distribute and simplify. So then this quantity here is a perfect square. So we can write that as x plus b over 2a squared plus the quantity c minus b squared over 4a. Okay, so that's how you complete the square. And then if you let u equal x plus b over 2a, to express the original quadratic in a simpler form, we can rewrite this as au squared plus r, where r equals the c minus b squared over 4a part. Okay, so let's actually run through an example here where we do this whole thing. So first, the expression x squared plus 6x plus 10. Can't really use u substitution the way it is, so I'm going to complete the square on it. So x squared plus 6x plus 10. I'm going to write it as x squared plus 6x plus 9 plus 1. Okay. And then x plus 3 squared plus 1. Now we can rewrite our integral. Now I didn't have to go through everything I went through over here because x squared plus 6x plus 9 is a perfect square. So if I rewrite 9, or excuse me, if I rewrite the 10 as 9 plus 1, I can group the first three together, first three terms, and that's a perfect square. Okay, so our integral becomes 1, or dx, over x plus 3 squared plus 1. And if I let u equal x plus 3, this starts to look like inverse tangent. So du equals dx. So this will become the integral of du over u squared plus 1, which is tangent inverse of u plus c. And if I back substitute, you'd have tangent inverse of x plus 3 plus c. Okay? So, a little trickiness there, but we're doing okay. All right, now I want to integrate functions that contain x squared plus x plus 1. So the integrand contains a quadratic expression there, so we're going to complete the square on the denominator. So let me do that over here. So we have x squared plus x plus 1. So if we complete the square on that, you'd have x squared plus x plus 1/4 plus 1 minus 1/4, which is going to be x squared, not x squared, just x, plus 1/2 squared, plus 3/4. Now that is not our answer, of course, but for part A, this integral becomes the integral of dx over x plus 1/2 quantity squared plus 3/4. Now I can let u equal x plus 1/2, and then du is equal to dx, and then this integral becomes the integral of du over u plus 3/4, u squared plus 3/4 rather. So this becomes 1 over square root 3 tangent inverse of u over, or excuse me, I'm sorry, that's square root 3 over 2, u over square root 3 over 2 plus c. Now if I back substitute and clean up the fractions, I'm going to have 2 over root 3 tangent inverse of 2u over root 3, and u was x squared, or x plus 1/2 over root 3 plus c. Okay, now we use the rule that the integral of du over u squared plus a squared is equal to 1 over a tangent inverse u over a plus c. Now for this one, the value of a was not 3/4, it's square root of 3 over 2 squared. You have to rewrite that 3/4 as a quantity squared. So this is our value of a right here, and that's why we had the 2 over square root of 3. Well, square root of 3 over 2, and then we multiplied by the reciprocal there. So for the next one, for part B, we're going to use a manipulation that causes the derivative of the denominator to actually appear in the numerator. So this is sometimes helpful. So I'm going to rewrite it here. So the integral of x dx over x squared plus x plus 1. Now what I'm going to do is multiply and divide by 2, or multiply by 1/2 and multiply by 2 at the same time. Okay? Because multiplying by 1/2 and multiplying by 2 are just going to cancel each other out. But it's getting me the integral in a form that I can now work with. So next thing I'm going to do is that gets the 2 in the numerator. The problem is that the denominator's derivative is actually going to be 2x plus 1. So to handle that, I'm going to add and subtract 1 in the numerator. So I'd have 2x plus 1 minus 1 over x squared plus x plus 1 dx. Okay, so now this is going to be, if I group the 2x plus 1, that is the derivative of the denominator. Then I still have that minus 1. But since it's all over the same denominator, I can split this integral into the sum of two integrals, but rewrite it with subtraction. So let me show you what I'm talking about. It'd be the integral of 2x plus 1 over x squared plus x plus 1 dx minus 1/2 integral of 1 dx over x squared plus x plus 1. All right, so we're not done yet. We're going to keep going here because this one's pretty cool. So I just move some things up here. Now, this integral right here is the integral of u prime over u. So this is the form of natural log. So it's 1/2 natural log absolute value of x squared plus x plus 1. And that goes with this integral, but I still have this one to take care of. Okay, so what I need to do now is this one, that second one, is actually the one I just did in the first example up here. So we know the answer to this integral is 2/3 tangent inverse, blah, blah, blah. So we can add that on down here, but it's being subtracted and multiplied by 1/2. So you'd have 1/2 times 2√3 over 3 tangent inverse of 2x minus or plus 1 over √3 plus c. So the final answer is going to be 1/2 natural log absolute value x squared plus x plus 1 minus √3 over 3, because the 2's here cancel, tangent inverse of 2x plus 1 over √3 plus c. Okay, now I know that one was pretty complicated and crazy, but hope that was helpful to you there. All right, so the next and last one we want to do in this example is integrals that contain 2x minus x squared or something of that form. Now, this is another quadratic expression, so we can look at perhaps completing the square, because again, you can't do u substitution directly, because if you let u equal 2x minus x squared, then you wouldn't have anything to substitute the du with. So the 2x minus x squared, we can rewrite that as negative x squared plus 2x. Okay, then we're going to factor out the negative 1, so it's x squared minus 2x. And then we're going to add and subtract 1 to that to make it a perfect square. So negative x squared minus 2x plus 1. And then technically you would subtract 1. Okay, it'd be like you would have a subtract by 1 in there. Okay, so you're adding and subtracting 1, and the net effect is you're adding 0. But we don't want it grouped with that perfect square trinomial, so we have to take it out of the parentheses, which is going to make it positive 1. Okay? Or you could think of, if we distribute this negative back in, it's going to make this one negative, which will cancel with the plus 1 outside. So this becomes negative x minus 1 squared, if we factor this trinomial, plus 1. Or we could write that as 1 minus x minus 1 squared. Okay, so we could rewrite this integral as dx over 1, or excuse me, square root of 1 minus x minus 1 squared. Now this looks a lot like sine inverse, very similar, where you have the integral of dx over square root 1 minus x squared equals sine inverse x plus c. Okay, that's the rule that we're dealing with here. But we have the x minus 1 quantity squared in there. So what we're going to do is let u equal x minus 1, du equals dx, and then things line up. We have integral of du over square root 1 minus u squared, which is going to be sine inverse of u plus c. So sine inverse of x minus 1 plus c. All right, guys, some crazy stuff there. I hope that was helpful to you. Reach out if you have any questions, and take care.